Moritz, presenting experimentation on networks. Please take it away. You have 45 minutes.
Thank you very much. So this is about innovation and its diffusion. So here's one innovation. It was an innovation 5 years ago, and it was so successful in Santa Monica that they introduced it here and there and there and there, and then it was everywhere in the world, right? So some innovations take off, others don't, right? So the paper is not about scooters, of course, it's about innovation and its diffusion more general. And, it's a first order economic question, right? So Moukir argues that innovation and its diffusion are both necessary and hence complementary for sustained economic growth, right? So from a production perspective, they're complementary. From a strategic perspective, they're substitutable, right? So Grossman and Stiglitz in their famous paradox argue that if all information that's relevant in financial markets can be gleaned from market prices, who would generate this information in the first place? Right? And so in centralized markets, we have a good understanding of that, right? There's auction theory, there's financial markets theory, and we understand how this sort of pans out in equilibrium. What we're trying to do in this paper here is to develop a theory of how this substitution, how this crowding out of private experimentation from social learning, how this pans out in a decentralized network setting, right? And so I'm not going to take a stance on the specific applications, certainly not scooters. So what I have in mind are the classical papers on learning on networks, right? So Grillicke's corn farmers in Iowa, or Coleman's doctors, who learned from their social contacts about this new thing out there. So the questions I want to address is I want to quantify this crowding out, right? How is it that social information crowds out the individual incentives to generate the information in the first place? How does this depend on the network and the position of the individuals within the network? And I'm going to talk also about the classical question of social learning. As this economy grows large, as there is sort of there's a potential physical for perfect learning, will it happen in equilibrium? So the model is going to be very simple on the learning side. Right, so experimentation is going to be good old perfect good news learning, right? And that's going to buy us a lot of traction here. It's going to allow for a lot of richness on the network side, right? So networks are going to be fairly general, and still will get not quite unique but unique-ish learning dynamics. Right? And in terms of the results, the two big results in the paper are going to be, well, how does network density, the number of links in the network, the connectedness, how does it affect the information that's being generated, and then importantly, the welfare. Right? So one shortcoming, of course, of the social learning literature is that it has focused very much on long-run outcomes, and we know in the long run we're all dead. Right? So welfare, of course, takes sort of a shorter, medium-term perspective, and the tractability of the model is going to allow us to talk also to welfare. Right? So information, unsurprisingly, is going to be decreasing in density as we can learn more. As there's more social information, individuals will generate less information, right? So aggregate information in the long term is going to decrease as the network grows denser. But welfare is going to be hump-shaped, right? So maybe not so surprising, because for welfare, a density is also a good thing, right? Because the denser the network is, the faster I'm going to learn. If I'm impatient, that's a good thing. Right, so that's the main result. So network density is bad for information in the long run. It has this hump-shaped effect on welfare. And then there's going to be other results that I may or may not get to, talking about sort of the effect of position within the network and the types of links that connect the network. Right, so here's sort of a Mickey Mouse version of the model, so the kind of behavior that's going to happen in equilibrium. And so here, this is my favorite network, the star network. And so initially, everybody's going to experiment because this new thing has prospect and the colors don't work out well here. So this would be gray dots on my computer, and this is a white dot here, right? So the peripherals are experimenting. The center, he's getting so much social information. The center is not experimenting. The center is waiting and seeing. And eventually somebody succeeds because, randomness, right? And so then at this point here, you can't see it because of the colors, I apologize. The peripheral guys get pessimistic because they have experimented for a while. They haven't seen a success. They give up on this innovation. Whereas these guys here, they have succeeded. And the center guy, he's seen these here succeed. So the center guy knows this is actually valuable. The center guy keeps experimenting. And at this point, the model becomes a standard SI diffusion process, right? So these guys, you would call them infected, or call this guy infected. And it's going to spread the innovation through the network, but it's going to take time, right? And so eventually everybody is going to be affected here, right? And so coming back to the question from the last slide about network density, what happens if I add a second central node, right? What if the star has a core of 2? And you might say, oh, that's going to be great because it's going to accelerate diffusion. And yes, it does, right? But you know, if the diffusion is faster, then of course the incentives of the peripherals to generate the information in the first place, that is going to decrease. And so that's the trade-off that the paper is speaking to. All right, so here's the literature. There's literature on strategic experimentation on the Clique, and you may wonder which of these models are we putting on network here. Not quite any one of them, right? So we're subtly but importantly different from these papers. In terms of the network literature, what this paper is trying to do is to be the equilibrium version of the seminal paper by Balla and Goyal. So Balla-Goyal is not an experimentation paper, right? It's a paper we're learning on networks, but the agents are myopic, right? So they don't purposefully experiment. They just sort of act on the information they've received in the past, whereas our agents are forward-looking, right? And so Balla-Goyal in the introduction say, you know, it'd be nice to talk about forward-looking agents, but it's just too complicated because of the network, right? And so how do we do it? Well, we have a simpler information structure than them. Also, the agents in Balla-Goyal, they're not just myopic, but they're also not fully Bayesian, because the assumption is that in Balla-Goyal that you only observe others. No, you observe others' actions and their outcomes. And of course, when you see their actions let you make an inference about what your neighbors have seen, what you yourself have not seen. Right? So that's like in the classical Bicchandani-Hirschleifer-Welch social learning model. And they just shut down that model. They shut down the channel. They say, yes, you observe other actions, but you fail to draw an inference from that. Right? You see others taking their actions and see their outcomes. You interpret this as an experiment and interpret the outcomes of the experiment rationally, but you're not drawing any inference from their actions. Right? So in that sense, they're not fully Bayesian. And the way we get around that is by just saying that our agents are not going to observe the actions of the others. Right? And so that might in principle raise other problems, but with the simple learning process that we have, we can address these. Let me give you the model, and then I'm going to pause. Here's the model. So the network is general. So capital G would be a random network. Lowercase g would be the deterministic network. Most of the applications are going to be deterministic networks. Sometimes the networks are going to be random. The learning game is as simple as they get, right? So every agent is doing their experimentation, right? So the actions, they're private, and the payoffs are private, right? So if my action has a cost of C to me, taking this in continuous time, and if the state is high, right? So this is the key assumption here. That's a perfect good news learning assumption. If the state is high, I may succeed at these times here, and then but only I get the payoff from this, right? So there's no payoff externalities, right? So when Iowa corn farmer try this new hybrid corn, I may get a bumper harvest. That doesn't affect your payoffs, right? So the only channel of interaction is informational, right? I see my successes, I see my neighbor's successes in this network, and from that I draw my inferences. But there's no payoff externalities. To summarize, okay, and the state is either low or high, and there's a belief about it. Initially, it's a common prior P0. And to summarize here, the problem that every agent solves here, agent I, is in general, it's a stochastic dynamical control problem. I'm choosing this control process here. Right? So at this level, it might be very complicated to maximize my payoffs, which are the payoffs from my successes at these times here, minus the cost of the experimentation. And it's going to simplify significantly on the next two slides. Yeah.
I see if you're blue, but not if you're gray. I sort of was the other way around. I see if you're green, but Like I see if you're experimenting, but not.
No, it's the other way around. I see your successes, not their experimentation. Yeah. Right. So my farmers, they don't see what seeds their neighbors are planting, but they see when the neighbor starts driving around with a new Tesla.
How do you observe your neighbor's successes, but not who your neighbors are?
Okay, so in the main case of deterministic networks, I know who my neighbors are. Right? In random networks, I'm literally saying I don't know what the realization network is. We could change that, as you could add that. We're not using that, so that's what I'm putting in the model. But you know, who are my neighbors? Who are my friends? Who are the people who might succeed? I don't know, how many friends do I have? I don't know. Right? So that's the perspective there. And you know, I mean, different applications that might be more or less realistic, and it doesn't really matter. I'm just not going to make use of that information, so I'm not putting that in here. And so I'm only having two polar extreme cases where I either know the entire network or I know nothing about the network. And you know, there's plenty of sort of in-between cases with asymmetric information. The most natural one, of course, would be where I know who my neighbors are.
An expectation is over my belief, it changes over time based on the observation of my success. Is that?
Yeah, that expectation is a beast, right? So it's about everything, right? It's about the network, it's about everybody's successes, and the successes are going to affect my actions. And you know, at this point, this is an enormous thing, right? I mean, yeah, the network and all the realizations. Yeah, but it's going to go away in a slide. Yeah.
So the simplification here is not seeing what my neighbor chose allows simplified space. So I don't have to infer that if I saw them try and fail, I'm inferring.
So with continuous time, it wouldn't even be clear what a strategy is if I observe my neighbor's actions, because I see their action and then immediately I might want to react to that, and you run into these measurability issues. Okay, so if the actions were observable, I would set this up in discrete time. But it would still, substantively, it would still be very difficult because, you know, let's say that sort of my second neighbor succeeds and my first neighbor starts taking the high action, and then I would start acting on that. But then, of course, my first neighbor might have a signaling incentive. It would get very messy, right? So making the effort private, it's clearly a tractability assumption. And you know, in applications, it's, you know, in some applications more reasonable, in others less so. And so I skipped the empirical papers, but there are papers on fracking and social learning by frackers and social learning by all extractors. And when they say, well, do I know what my neighbor on the neighboring tract is doing? They say, well, you could kind of learn it, but it'd be really difficult. You'd have to go to these archives and sort of try to decipher this information. And, you know, maybe at some point you're going to learn it, but then the model they assume they don't. Right, so I'm taking the same assumption that the empirical IO papers are taking.
Is that a Poisson process of successes?
Yes.
And what's R?
What's I?
R. It's just the letter R.
The R, that's the interest rate.
Okay.
Yeah. Just my impatience.
Okay.
Sure. All right. So, I mean, Bunny goes into the hat. Bunny comes out of the hat. If I see a success, I know what the state is, because the low state never leads to successes. Right? So once I see the first success, game is essentially over. I know the state is high, and since I assume that x is greater than c, I'll take the high action forever after. Right? So if either I succeed at time t, or one of my neighbors succeeds, I'm done. Right? So the game really only happens for me before that first time. Right? So we can focus everything on the time before my first observed success, which in general, in a general network, is going to be person specific. Here, y is going to be my continuation value of taking the high action forever after when I know the state is high. Right? So I'm going to truncate the game usually in my pair of expressions at that time. And then we're going to call my own action before learning the first success. I'm going to call this lower AT naught for not having observed a success. And the important thing, of course, the social learning and what I get from others, that is going to be the BT, right? So my expectation over my neighbor's actions, conditional on me not having succeeded and my neighbors not having succeeded yet. And I'm going to call that thing here my social learning curve. That's the rate at which information hits me, and it makes sense to condition on the high state, because on a low state, no successes ever occur anyway. Right? So that is sort of reasonable. That's a reasonable measure of social learning. And it's going to be capital B in a second, then it's going to be the integral of lowercase b. Right? So that's the rate of social learning, and then it's going to be cumulative social learning.
And this expectation is also with respect to the.
Yes. Yeah. So if the network is unknown, right, and I wonder, are there any friends out there? I don't see successes. I get pessimistic both about the state and about my social status. All right. Okay. So Bayes' rule, right? So if I don't see a success, I get more pessimistic, right? So that's the aggregate learning that has happened before time t. When I will stick that into Bayes' rule here, and that gives me my posterior, right? So I start at P0, and then I get more and more pessimistic as all our experimentation fails to succeed. And the stochastic control problem has now become a deterministic control problem, because I'm truncating everything at the first success. Right? So what's in the integrand now here at time t, I'm experimenting. Well, if I'm experimenting, I may get the success myself. I may get the success, that gives me x. It also gives me the continuation value of y. If others succeed, I don't get the payoff directly, there's no x here, but I can take the high action forever after, so I do get the continuation value. Right? And so now I have to discount the future, not just at my impatience rate, but also at the rate that we are observing successes, because that gives me my continuation value. So I've put sort of the continuation value in the integrand, and so I have to correct for that in the discount factor. Okay. So this is sort of step number one.
I'm sorry, I never really understood that. It's like the third time. But what is happening when you're putting it in the discount factor? Is that the time effectively? I guess is that the time at which it occurs? Is that why it's in the exponent, or?
So mathematics is integration by parts.
Okay, so I guess you're doing an integration by parts step there that's not supposed to be entirely transparent.
No. Mathematically, it's not transparent. I think economically it's intuitive, right? That if I say that at some time when success arrives, I collect my continuation value, why I'm putting that into the integrand, and effectively that's truncating the expression here, my future payoffs at that time. Right? And so you can think of R, of course, you can think of R both as the interest rate or at my death rate, where I die and I don't get future payoffs. But, then this is sort of the rate at which I die, and that's the rate at which I learn and get my Y. And so that's how it makes sense that it appears here together with R, because it is the same, the rate at which the problem ends. All right. So I transformed a stochastical control problem into a deterministic control problem. I assumed that, right, by making perfect continuous learning. Here's step number 2. To solve this deterministic control problem, I choose a cutoff. Right? So the optimal response, no matter what others are doing, is to choose a time, 17. And at time 17, if I haven't observed a success, I'm going to stop experimenting. When I say stop experimenting, that's of course conditional on not having observed a success, and that I don't stop forever. I sit there, I wait and see, and if somebody else succeeds, then of course I jump back in and I start again. Right? When I say stopping time tau, it's conditional on not having observed a success. Right? So why is a cutoff strategy optimal? Why would it not be optimal? Right? I'm getting more pessimistic over time. I'm failing, everybody else is failing. I'm getting more pessimistic. Why would I sort of not experiment now, then later when I've gotten bad information, why would I start later? And that's essentially the proof, right? So if you write the proof, if you think of front loading a little bit of experimentation, right? So if you think, well, maybe I should sort of wait a bit and then experiment later. If I take that little bit of experimentation from later and pull it forward, that's going to be beneficial for me.
How is this incorporate a wait and see strategy like in the start? What a cutoff means I always experiment until I decide to stop.
So the wait and see is after I've stopped and I don't restart unless I see something. The wait and see strategy, wait and see interpretation of the strategy is that I'm waiting for a success, and after a success I start. And so what this is saying is I would never restart if I don't see success. Only if there's good news.
So this doesn't
Perfect
fully
news.
characterize my strategy then, because you don't know if I'm either waiting or experimenting at times less than tau.
So this fully characterizes my strategy.
So I don't understand the strategy.
But this is saying if I don't, I'm going to experiment, I'm going to take the high action until time tau no matter what. After time tau, I'm only going to experiment if I've seen a success.
I see.
Do I need to experiment or can I adopt? I see a success. In real world applications, you would think that I would just adopt and not experiment.
Very good. That's what they do. But adopting means you know, planting these seeds as a farmer, and then they only pay off at random times. Right? You don't get the payoff right away. You're getting them with this croissant delay.
But then what is the experimentation? That's
It's just language, right? I mean, there's really just a high action, the low action, and I'm calling it experimentation when you're doing it while you're uncertain. After you're uncertain, you know, you could still call it experimentation, but in a way, you know the state.
So,
It's just language.
just to clear, so the strategy is you wait, you tried for tau steps, and
Yeah.
then if you haven't succeeded, then you stop, and then if you see a success, then you restart experimentation and you never stop until you succeed. Or don't.
Even when you succeed, you
You-
take the
well,
high action
actually-
forever.
Yeah.
And, you know, there would be an isomorphic model where you only succeed once. Right? So, you know, you'd have to sort of renormalize payoffs, but that would be the same model. All right. Okay, so cutoffs are optimal. That, of course, is very important, right? Because I started with sort of a complicated stochastic control problem. And now I'm saying you're just choosing a cutoff, right? So what's the first order condition for the cutoff? Right? If I increase the cutoff a little bit, right? So this is my payoff here. This is my strategy. That's my social learning curve that comes from others. If I raise my cutoff a little bit, what's the payoff from that? You know, with probability p tau at time tau, the state is still high, right? So that's my posterior belief. If I experiment, I may succeed. That's getting me the x here, and I shouldn't have shown you this. Let me give you a simpler version of this. Let's assume that the social learning curve B is constant, that I'm getting the information from the others at a constant rate. So then the net benefit of experimenting would be p tau times x plus y. Right? So if I experiment, I'm getting my payoff x, and I'm getting the continuation value y. There's a cost of experimenting c, of course, and then there's the opportunity cost of not learning from others. Right? When I learn myself, I'm not benefiting from their information anymore. If they're experimenting at a constant rate b, my value from learning from them would be p tau times b divided by b plus r. Right? So if I'm learning at a constant rate from the others, the value of that is going to be discounted because, you know, I'm only going to learn from them in the future. And you know, a little bit of algebra shows you that b divided by b plus r is the right expression. I'm pulling that in here, then it becomes r divided by r plus b times y. And, you know, now more generally, if the b function is not constant, right, in general it's not going to be, you know, then it's going to show up in the exponent here.
What's the meaning of x and y?
X is the payoff that I'm directly getting when I succeed, and y is the continuation value from taking the high action forever after in the high state.
P tau is the probability.
P tau is the posterior belief that the state is high. What we see here already is that, so this formalizes the crowding out idea. Right? If there's high social learning, if I'm getting a lot of information from others, you know, the exponent is going to be large, the integral is going to be small, and the benefits from experimenting are going to be small. B is equal to 0, if there's no information from others, solving the single agent problem, and then I'm experimenting for a long time. In belief space, how does the optimal strategy look like? Well, if my belief is higher than the myopic cutoff, then I always experiment because myopic is the right thing to do. And then on top of that, there's the information value. If I'm below the single agent cutoff, right, for an agent who doesn't have social information, that person wouldn't even experiment if he didn't get social information. Now, when we give him social information, that's going to reduce his incentives, right? So down here, there's certainly no experimentation. In between here, it's going to depend on the rate of social information. So a lot of social information, we're going to be up here. With little social information, we're going to be down there. So a rise in social learning, if I get more information from others, that raises my value. That's just Blackwell's, the trivial direction of Blackwell's theorem. And it decreases the incentives because it shows up in the exponent here. And so it decreases the incentives and therefore the experimentation, right? So the more others experiment, the greater the social learning curve be, the less I'm going to experiment myself. Way behind time. All right. Okay, so I got to skip this here. So I've shown you how the social learning feeds into the optimal response, or feeds into a cutoff that's characterized by a first order condition. And what's missing now is, well, how do these individual experimentation choices, how do they aggregate into a social learning curve?
So how is the cutoff time?
Cutoff time, that's right, yeah. All right, equilibrium exists. It's not, we don't know whether it's unique or not, but it's not going to matter. All right, so here's the clique, right? Everybody is connected, and we get a unique equilibrium. Right? There's full crowding out, that's known in the literature. So capital tau, tau bar here is a single agent experimentation. If I was doing this by myself, this is how much I would experiment. And there's full crowding out in the sense that all the agents, they're splitting this experimentation equally among themselves. The fact that there's full crowding out, that's known in the literature, that just comes from the optimality condition of the last person who experiments. The last person is essentially solving the single agent problem, and therefore there cannot be more experimentation than the single agent problem. What's novel here is uniqueness, right? So in standard, public good games on networks, there's a gazillion of equilibria because the effort is perfectly substitutable. And what's different here is that we are sort of providing this public good of information dynamically, and we care about the future, right? We're impatient, right? And so if you're trying to cook up an asymmetric equilibrium, what's going to bite you is that at the last time, when the last person starts experimenting, everybody's indifferent. But I told you before that front loading is beneficial, right? So if anybody doesn't experiment until the very end, he would be indifferent about experimenting at the very end, and then he'd front load and benefit from that. So that unravels all asymmetric equilibria, right? So that, of course, is only a starting point, the clique here. So here's a more interesting network, right? The infinite line, I think what is this, a large finite circle here. And let me just, this is just how the contagion spreads. Let me solve this thing here, right? I'm going to take Iris's position here. Iris observes John, but doesn't observe Kata. Right? And so after time tau, up until time tau, everybody experiments. We know that in equilibrium. After time tau, Iris thinks, well, is John experimenting? Right? And he wouldn't be experimenting if he hadn't seen anybody succeed. So the only way that John would be experimenting is if Kata has succeeded. So Iris has to think about, has Kata succeeded, conditional on me, myself, and John not having succeeded yet. Right? So we're going to solve this conditional probability here. We're going to stick this into Bayes' rule, and we find that it's this expression here. And the amazing thing is it's constant. Right? So you might have thought that this would be increasing over time because there's Kata and Lily and all the others in the chain there, and they're succeeding over time. So you might think that the probability that John eventually sees it would be increasing, and that's true, right? So there is a force that's saying that social learning is going up, but at the same time, Iris is conditioning on the fact that John has not succeeded yet, right? Because we're fixing the network, right? And the fact that John has not succeeded yet that's bad news about anybody else having succeeded. And Bayes' rule is telling us is exactly these two effects exactly cancel. And so just like in my example there, the social learning curve is actually constant. Right? And so I can stick it now back into the equilibrium condition from before, and that characterizes my equilibrium in the infinite line.
In this model, if you had everyone experiment for epsilon periods and then stop unless they succeeded, then you would sort of, everyone would very quickly learn, right?
Not very quickly, right? I mean, they would eventually learn. In this model, in this network?
Yeah.
But if epsilon is small, and every single person succeeding is a very small probability. And yes, somebody will succeed, but then it has to sort of feed down the chain. So it might take a long time. As epsilon goes to 0, the time at which I observe the success is going to go to infinity stochastically.
But why does it take time for the?
So when Kata succeeds, John starts experimenting, but he only succeeds at an exponential rate. Right? So expectation is going to take 1 period time 1 for John to succeed, and for this to feed to Iris, because you only see the outcomes, and the outcomes are.
No, I understand. But my proposal was everyone experiments for epsilon periods and then stops. Then you have infinitely many people who have succeeded, and then after the time when you stop, unless you see a success, the information can sort of spread instantly, right?
But in this network, yes, infinitely many people will succeed, I agree. But the typical person who's going to succeed is going to be far away from me, because a very small percentage of them succeed.
Okay, I think I'll ask you later.
Yeah. All right. Let me think. Okay, so my welfare and my information measure. Information I'm just going to measure by the aggregate information that agent I gets in the very far future. I'm going to take the minimum over all agents, just to make sure you're not cheating and giving me a network where one person learns and others don't. For the welfare, I'm going to take the same, and that could be infinite, right? So we've already seen a network, the infinite line. The agents learn perfectly in the long run. For welfare, P0 times Y, that's the value you would get if I just told you the state immediately. Right? That's the best thing you could ever get, but that's certainly an upper bound. That one's not tight yet, right? Because that's the value if you learn perfectly immediately. But the thing is, not everybody can learn perfectly immediately, because if you did, you wouldn't experiment. And if nobody experiments, there's no information from others to learn from. Right? So somebody has to be doing the work here. Right? So, and there's an upper bound on the value of an agent who's actually doing any experimentation. I skipped that step for time reasons, but it's this expression here, and it may be lower than that. Right? So that's also an upper bound on the value of experimentation, on the value of the worst of agent here. Right? So we're going to call this here our second best benchmark, and that's justified by the fact that I'm going to show you in a moment that we can achieve it. Right? So there are networks where all the agents are actually getting this here. Right? So that's a tight upper bound. All right, skip that. So how do the examples fail in the clique? Learning is very fast. So this is the aggregate learning curve, capital B here. So initially we learn fantastically, but it stops. Right? So there's too little information. The line is the opposite. Right? In the line we eventually learn, but it takes so long. Right? And so we're impatient. Right? We don't like the epsilon thing that Krishna proposed. It's terrible. This is worse than the clique. Right? All right. Okay. So finally, with 10 minutes to go, here comes the real network, the angry network. The angry network is supposed to look realistic, and it's a realization of the configuration model. Right? So the configuration model is my favorite model of random networks. It works as follows. Agents have stubs, and then stubs randomly connect into links. That's it. Right? So that really is the configuration. That's in general, you could sort of say people have different degrees, right? Here, make and regular. I got to say a little bit about the things that might go wrong, right? So two of my stubs could connect to each other, and then that's not really a link, so I'm going to scrub that off. Could be that I have two links to Ben, but all these things are pretty unlikely if the network is large. right? And so the configuration model works nicely as I goes to infinity. The network is symmetric enough that equilibrium is unique. So tau I and Vi here are my unique equilibrium experimentation times and my equilibrium values. Right? And so now what I want to do is I want to characterize information and welfare as a function of network density. Right? So in any finite network, I know what network density is. It's just Ni, the number of my stubs, which is approximately the number of my links. Now, as this goes to infinity, you could say, well, just think about sort of the configuration model where everybody has 17 links, right? So that would be 17 down here, take it up to a billion or so. And then at some point we're at infinity, but we can go beyond, right? Because we could say that, maybe you're connected to 1% of the agents out there, right? And so then as we shoot the number of agents to infinity, the number of my neighbors is not just infinite, but it's a percentage of the population, right? So there's a spectrum over here that's in a way more than infinite, right? And so in between a relevant range, and that shouldn't be too surprising if you studied your random networks, is the logarithmic range, where the number of neighbors is proportional to the logarithm of the agents out there, right? And so this turns out to be the right measure of network density, this somewhat awkward spectrum of the finite range, the logarithmic range, and the infinite range.
So n
in
is-
that,
so just
yeah.
The symbol n is like degree bit more. Each ni with ni total with subs.
That's the total degree. Ni is a total degree. And lambda is, well, rho is easier. I mean, rho is, okay, just look at this here. Rho is the percentage of people that you're connected to. Right? And so this is just a complication because, if you have too many stubs, then actually you will start wasting stubs on connecting twice to them. That's just the 1 minus e to the minus. It's just correcting for that. This is really the number of things to them. Right. Okay, so this is the right measure of density as shown by the theorem here that limit information and limit welfare are indeed a function of the limit density as defined on the last slide. Right? So for any sequence of networks with existing limits, right, where both we're converging one of the three ranges here. Any such sequence of networks has the same limit information, the same limit welfare. Right? And so the limit information is decreasing. It's not so surprising. Right? I mean, if you're better connected, you learn faster, and that drives out your incentives to experiment yourself. Right? So what the theorem is telling you is that there's a threshold, and it's in a logarithmic range, at which point the crowding out is going to be so strong that in the aggregate, as the number of agents grows to infinity, the aggregate information still stays bounded. Right? So below the threshold, in particular in the finite range here, the information is going to aggregate just like in the infinite line. So the infinite line is down here when u is equal to 1. And if the network grows too dense, if there's too much crowding out, then eventually that's going to, we know already, right? I mean, if we connect to everybody, if rho is going to infinity here, then we're approaching the clique. And in the clique, we know we're not aggregating information because there's full crowding out. Right? And so what the red line is telling you here is that there's a threshold in the logarithmic range where asymptotic learning starts to fail. Right? So that's the red curve. The blue curve is welfare. Right? And so welfare, as I was saying in the beginning, for welfare, density is a two-sided sword. Right? Because on one hand, we want to have density because it accelerates the learning. That's important because we're impatient. Right? But at some point, if the network grows too dense, we're already learning super fast. So at that point, it really becomes a question of how much information do I learn. Right? And so as the network grows denser, total information starts to decrease, and then the welfare also decreases here. Right? And so we see that the second best welfare benchmark, V star here, is achieved precisely in the logarithmic range, really I should be saying, in the range between finite and proportional degrees. Right? So second best welfare is achieved if and only if the degree explodes asymptotically and the absolute degree explodes. Right? So nu is equal to infinity, but the proportional degree, the proportion of nodes that you're connected to, if that vanishes. Right? That's necessary and sufficient for the second best welfare benchmark. What is sigma star here? In this range where the network is already pretty dense, we're going to learn asymptotically at the deterministic time. Right? There's going to be a time at which all the social information is going to hit me. Right? So social information is BT function. It used to be a function. In the infinite line, it was a constant function. In this range, it's going to become a tsunami. Right? So it's going to hit me. There's going to be this one time when all the social information is going to come crushing down on me, and that time is sigma. And if that time sigma star is such that learning perfectly the state at time sigma star, if that social information makes me indifferent about experimentation at the initial time, at time 0, well, that defines sigma star. Right? And so you see that this is kind of the right condition here, right? So if initially I'd have strict incentives to experiment, then everybody would do it, and there would be a lot of information. It would hit me much earlier. If this was negative here, so if this was a less than C, then initially nobody would experiment, and there wouldn't be information coming around. So that's precisely the right time at which sort of the information, sort of this finite amount of information that's going to come at some future time is exactly going to make me indifferent at time 0. All right, I'm 4 minutes. All right, okay. So what else is there? Including questions. All right, okay. What else is there? These networks, right? So the random networks, they look very general and realistic. On the other hand, in the random networks, every agent is the same. It's kind of like macroeconomics, right? It pretends to be very general, but really every person is the same, right? And so in that sense, this network here, even though it looks sort of much more like an example, in a way it's richer, because the peripheral agents, they're different from the core agents, right? And so that generalizes the star, and what we can show is that the core agents, they experiment less, they're better connected, they have more social information, and therefore they do less and they're better off, right? And so then as we let the periphery grow large, we can do the exercise from the random networks again, we more or less get the same result, right? So this is sort of the density of these core periphery networks, where now we're measuring the core size, which is sort of density. And so we see that again, the red curve is the information is decreasing in connectedness, whereas the welfare is hump shaped. Type of links. Right? So I was talking about density of links. How does more links affect information and welfare? So here the question: how does a type of link affect information and welfare? Right? You could say that Twitter is maybe a directed network, LinkedIn might be an undirected network, and other networks might be clustered in the sense that my neighbors are also friends amongst each others. Right? And so what we can show here is that sort of holding the degree fixed, directed links are better than undirected links, and undirected links are better than clustered links. But the effect is not large. Right? So one more link reverses the order. Right? So the undirected 5 network is better than the directed 4 network, and the triangular 6 network, where you have 3 triangles, that's better than the undirected 5 networks. Absolutely, right. And so the interpretation of that, well, does the type of link matter? As in Buehler-Klempner, it is, if the degree is large, it doesn't matter. But if the degree is small, one more degree might be a big deal. Right. So wrapping up, I have a tractable model of experimentation on networks. The way we get that is by making the learning as simple as possible, right? And so that's what Perfect Good News does. And that allows us to sort of, get a characterization of best responses in terms of cutoffs that then allows us to characterize the learning curves in all sorts of networks. The hope is that we can put this into a bunch of other models, right? And so there's a sizable literature out there about learning on networks that really is public goods on networks, right? Where you have this reduced form modeling of networks where, in the model it's really just a public good. Right? So I'm thinking of Romeo Cranton and Galeotto-Goyal. And so now here is a Bayesian model of learning and networks, where learning is really sort of our Bayesian interpretation. And you already see differences, right? In Galeotto-Goyal, the center does all the experimentation, the peripherals free ride on it. Whereas here, it's the opposite way around. Right? The center is what they call a passive connector, not doing any experimentation themselves, but brokering the information, if you will, between the peripherals. Right? And so the hope is that you can sort of more broadly use this model here to investigate sort of the specific features of information in networks, and what's the same across public goods and what's specific for information.
We have time for one question. Sounds we can have questions for lunch. So thank you very much.